Hi, this is the title of the talk, and I have a collaborator from mechanical engineering department by the name Rohit Misra. Rohit, say hi. Show wave your hand, okay? Now, next slide, I'm giving an outline of the talk quickly. So these outlines you'll see in one after another slide, so I'm not going to dwell much on this. So let's move forward. So this is the motivation. So this problem came up in the context of EOR by surfactant polymer flooding, on which I've given talks in the past. So a typical setup I'm showing in which a sequence of complex fluids is being injected to displace oil in the reservoir. And these complex fluids have components such as surfactant polymer. So actually this is a non-Newtonian flow through porous media. So right now we have encoded a typical model based on Newtonian physics. So I'll show you that first in the next slide. So this is a Newtonian model. The top equation is a system of transport equations for three components: saturation, concentration of polymer C, and concentration of surfactant gamma. The next equation is the elliptic equation or the pressure equation, which comes from Darcy's law. So they are coupled. And in these equations, viscosity of the aqueous phase plays a big role, and the aqueous phase viscosity currently in the code which you have developed, which we'll talk in a minute, is based on this viscosity model. Aqueous phase viscosity depends linearly on the concentration of polymer. So you see it doesn't depend on the flow at all, the deformation tensor of the flow. That means it is really not a Newtonian, non-Newtonian model. This is really a Newtonian model. So we have published already papers on this, and some of the papers I've listed. One of the paper I've listed here, which gives you the numerical method and simulation results. And the numerical method that we have used there, I'm going to briefly outline in the next slide. The numerical method that we have developed is called hybrid method, based on discontinuous finite element and MMOC method. The pressure equation is solved by discontinuous finite element method, and the transport equation is solved by MMOC. And the convergence proof of this method that I talked about is also published, which is the reference number 2 on this slide. And so all these publications are based on Newtonian model, meaning the aqueous phase viscosity depends only on the concentration of polymer and nothing else. Now we are trying to improve that viscosity model to include the shear thinning effect. That means that viscosity model should depend on shear rate and all that. So next slide, we are going to show you what we are doing now and what we have done. So this is a parallel model, viscosity model. Viscosity depends on two parameters, epsilon and n, and gamma dot is the shear rate. Epsilon and these parameters are not constant in the flow. It depends on the concentration of polymer. And since the concentration of polymer is evolving in time due to the previous page equations, this epsilon n also will evolve in space and time. So basically this parallel model is not static, it is data driven, and it is point-wise, it is different in some sense in the entire flow domain. And gamma dot is shear rate, which you calculate by the formula which is given below, and this you can easily derive. So, and this also is computed locally, as you can see, it depends on the velocity gradients. So next slide, we are going to show you how we get the epsilon and n, the data driven. So there are experiments available. We took the experiments of these three authors, Lindner, Bond, and Mueller, in which they have had some data table of n and epsilon, these two parameters as a function of concentration, so that those data we have taken a curve fit of those data with regression analysis, which Rohit has done, and he gets this nice curve fit of those data, which gives a continuous function of n and epsilon as a function of concentration. And we have used this to calculate these parameters as concentration keeps changing in the flow field and in time. So next we are going to show the simulation results. So here first we are showing the viscosity, the viscosity, how it is changing with concentration and n. No, how it is changing with shear rate. So these are the plots of viscosity versus shear rate at two different initial polymer concentration. It shows that it's really shear thinning fluid. It is modeling that, and these calculations again have been done by Rohit. And it is also showing as the higher polymer concentration, and we have retained down here higher viscosity. We have at higher IPC, that's where it should be, and the lower viscosity at higher shear rate. So that shows the shear thinning behavior. The next slide is going to be taken over by Rohit now. He's going to talk about the rest of the slides except the last one. Rohit, can you take it from here, please?
Sure, yes, Professor. So here we are discussing the results for all our shear thinning simulations. So first off, we noticed two different major observations from the current slide. So first was the finger width dependency on the injection rate, and the second was the dependency due to initial polymer concentration. So from our observations, we found that the wider fingers were observed at higher injection rate at water breakthrough, and higher initial polymer concentration leads to wider fingers. And from the simulations, you can see that the IPC 0.001, which is on the right, which is the higher polymer concentration, moves faster due to the viscosity ratio. And then the water breakthrough due to a lower injected polymer concentration comes through. It's important to note that both are being injected at the same rate, which is 2, and these are all non-dimensional values. From the graphs, it's pretty much given, and the observations are what I discussed. And Professor, if we can move to the next slide. So since finger width are not a very good comparison of the results, we used cumulative oil recovery for doing our comparisons. And we received like interesting results from our simulations. The first interesting result was that the optimum COR was achieved at an intermediate initial polymer concentration and injection rate. And also another important result was at higher injection rate, the COR is inversely proportional to the IPC. And this effect is mainly due to the competing effects of the shear thinning effect and the stabilizing effect of the increasing IPC, which results in the lower COR. So another important aspect of this project will be to look into how dynamically changing injection rate and dynamically changing IPC will result in another optimization problem for the cumulative oil recovered. And this would be actually very useful in the practical domain to understand how to inject polymer within the tertiary oil recovery process. Professor, if you can move to the next slide. So apart from the shear thinning model, we have also implemented the Todd logs of mixer model. So we have 6 frame here. The first 3 frame represents constant omega, which is a mixing parameter, which we will come to in the next slide, and with varying concentration. While in the second row, the bottom 3 frames show varying omega but constant concentration. So you can see that the second row actually represents how well mixed a polymer is. So here the important point is when omega is 0, we have isolated polymer, and with omega equals 1, we have a segregated polymer, which is completely mixed. So the viscosity model here represents how the TL mixing model is affecting the viscosity. And as I said, the mixing parameter is bounded between 0 and 1. So 1 represents a fully mixed water and polymer solution, and omega equals 0 represents a fully segregated one. So all these equations are representing the way the TL model is set up. And the final, the equation at the bottom represents how omega and all these parameters affect the final aqueous phase viscosity. Here I'm showing the major effects that we see in by applying the Todd-Longstoff mixing model. And in the first row, we are representing how the difference in viscosity field occurs a long time from time equals 5, 10, 15, and 20. So the results that are plotted is actually a difference between two simulations. So this is a difference between the viscosities at omega equals 1, where the polymer and aqueous phase are fully mixed, while at omega equals 0, it's fully segregated, fully isolated. So in this, you can see that the mixing happens over time, and at higher time steps, you can see more mixing, and that's where you see a higher difference in the viscosities due to mixed and unmixed polymers. And in the bottom graphs, you can see that at time equals 5, we have almost an overlying viscosity. And eventually at time equals 20, you see some differences in the mixed and unmixed simulations, for the viscosity of mixed and unmixed simulation. So to summarize all these results, the major results were the competing effects of the shear thinning and mobility ratio, which we saw from the cumulative oil recovered. We also noticed that the finger width is not really the best parameter to assess the sweep efficiency. And we noticed that higher IPC leads to wider fingers at breakthrough. And also at higher injection rates, we saw wider fingers. Cumulative oil recovered is not really a monotonic function of IPC and IR. So that's where this project becomes really important, because we need to find that optimum IPC and IR to figure out the maximum cumulative oil recovered. And a Todd-Longstoff mixing model, although a very important model to incorporate the porosity into the viscosity of the domain, does not really affect the viscosity significantly, except for at the interface. But we believe that if we apply this Todd-Longstoff mixing model along with the shear thinning model, we'll be able to see much more interesting results, which will be part of a future work.
So here I'm taking over from Rohit and showing the basically main key deliverables that we have from this project, which we call main conclusions. So what I'm saying that we have the Newtonian model that we showed for multi-phase, multi-component flow, and the shear thinning effect has been encoded in our MMOC DFEM base code. This new code has been tested and validated. The numerical results obtained agree with experimental results qualitatively. Simulations with Todd-Long mixing model is in progress, and most of this work is being carried out by Rohit. In collaboration with Saurabh Datta, we are also developing a model for including dispersion effects, and then we'll include this effect in the code. We are also implementing a multi-scale model, and we are also working on improving our numerical method for higher accuracy. And thanks to Siam. And if you have any questions, you can email at this email address. And thank you. Bye.
Thank you. Bye.
Should I end meeting for all, or is it not getting recorded, right? I guess.
Professor, it's still recording. You can stop the recording. There should be an option to stop recording.
Well, let me end meeting. I'll come back.